Yeah, it's Chili here. Let's take a look at the solution to the coding challenge number 2. But before we do that, we got to take a look at our grand champion. So drum roll, please. It was pin drought with 47 milliseconds. Pretty fucking good. Congratulations. I made a nice little chart here. You can see, a couple of people were in the 1 second range. This is in units of microseconds, by the way. So you got a couple of people in the 1 second range. Mostly everyone is in the 100 millisecond range, and a couple of people in the tens of millisecond ranges. If we do another graph, we cut off SH and Blade. There we can see a little more detail here and how the different answers stacked up. Obviously, smaller one is better. So big congrats to especially Pin Drought and also Warm and Fuzzy. You guys made some fast code, but really just everybody. Because it was definitely a more difficult challenge than the one we had before, and we had a lot. Actually, I was surprised at the amount of people who submitted answers, maybe around 30 or so. And out of that, 11 people got the right answer. So congratulations! Just getting the correct answer is a big accomplishment in and of itself. And I hear you guys asking, well, what about you, Chili? What did you do? Well, I can just scroll up here, and we can see Chili did it in 670 microseconds. So try not to pat myself on the back too hard, but I'm pretty pleased with that result there. Just to put things in perspective here, this is most of the people compared to Chili, and here is the top 2 answers compared to Chili. Yeah, I fucking dunked on you bitches. Woo! No, really, I'm just being an asshole, but yeah, so probably a lot of you guys are wondering, well, Chili, how did you do it? First of all, how do you do it just at any speed? And also, how did you do it so fucking fast, brah? And, well, I'm about to give it to you. X is going to give it to you. So first I'm going to go over the basic theory of how you solve the problem. Then I'm going to go through my code, starting from my first iteration up until the most advanced version. And all the code is going to be up on a repo on GitHub. I'll put a link in the description so you can check the code out for yourself if you're interested. Or if you just think I cheated and you can benchmark it yourself, I guess. Now, before I get into the nitty-gritties of my implementation here, I just want to make one simple but very important point. Now, I have incredibly fast code here running in about 670, 680 microseconds to process this 7,000-digit number. Look at this shit. What do you see here? Class big num. You see a lot of operators and shit. Let me just go outlining, collapse the definitions. You're seeing a lot of C++ bullshit in here. You know what I'm saying? You're seeing, std vector, overloading operators with my big num here. You're seeing templates. This is very C++, and it's very fucking fast. And I just want to highlight this because there's a lot of assholes out there who are going to like to teach that, C++, you can't use that. It's too slow. You've got to code in C for real speed. Or the real assholes who tell you, nah, man, you got to code in assembly if you want the real. These people are very stupid. And I mean, if you see one of these people, don't punch them in the face. Don't have an argument with them. You just break the wrist, you walk away, because they're not worth your time. These people are beneath contempt. Assholes who try to tell you that C++ code and speed are mutually exclusive, they deserve your pity more than anything. But still break the wrist. Anyways, if you didn't recall, the quest was I give you a number, let's say 12, and you got to reduce that number down to 1 using only the operations of add 1, subtract 1, or divide by 2, but you're only allowed to divide by 2 if the result would be a whole number. So you can't divide an odd number by 2, basically. So first of all, you want to do this in the minimum amount of operations possible. So every operation you want to be reducing by the most amount possible. Now, if we compare, obviously adding isn't going to stack up very well because you're making the number bigger. So let's compare division and subtracting, and you'll see, obviously if the number is 2, whether you subtract 1 or divide by 2, the result is going to be 1. So they're equal if it's 2. If it's 4, obviously division is going to win. It's 2 operations of division compared to 3 of subtraction, and so on and so forth. As the numbers get bigger, division gets more and more tastier. So what you want to be doing is you want to be dividing whenever possible. So the rule is, if even, then divide by 2. That's the first thing. Now, you might be asking yourself, well, why would I even want to add, though? I mean, that's a dumb operation. That's actually taking me further from my goal. So I can just ignore adding, but that would be very short-sighted. So let's take a look at a simple example here. Let's take the number 15. So what if we were doing 15, but we only had the option of subtracting and dividing by 2? Well, 15 minus 1 is 14, divided by 2 is 7, minus 1 is 6, divided by 2 is 3, minus 1 is 2, and then that reduces to 1. You've got 1, 2, 3, 4, 5, 6 operations here. Now, what if you started off by adding 1? Now you're at 16, you divide by 2, you're at 8, you divide by 2, you're at 4, you divide by 2, you're at 2, and then that reduces to 1. That's 1, 2, 3, 4, 5 operations. Here you can see that by adding 1, we've actually reduced the amount of operations that we have to perform. Now, it turns out for these kind of challenges, I often like to look at the number in binary. And there's a number of reasons for this. One of them is a lot of operations are a lot faster if you use binary bit twiddling operations. Let me give you an example. Divide by 2 in binary would just be, well, let me show you. Let's take the number 8, which is just 1, 1, 0, 0, 0. If I divide 8 by 2, the result is 4, which in binary is 0, 1, 0, 0. And if I divide that by 2, that's 2. If I divide that by 2, that's 1. You see a pattern here? Shifting right, 1 bit divides by 2. Shifting left, 1 bit multiplies by 2, by the way. And a lot of algorithms, you can gain a little bit of boost if you start thinking about them in binary, because that's the way the machine thinks about them. Not always, but sometimes. And I like to think of this one in terms of binary for a number of reasons. So I mean, if you think about division by 2 as shifting right, then let's look at some numbers here. So 0, 0, 1, 1. All right. So you can subtract 1. That would get you 0, 0, 1, 0. And then you can shift right. And now you're like this, right? So that's 2 operations. You could also just subtract twice and get the same thing. So there's no real bonus in division here. But if you look at the number 0, 1, 1, 1, obviously if you add 1 to this, you're going to create a whole bunch of zeros, and then you can just shift that shit in, pipeline, just bam, 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 and you're done. It turns out that 0, 1, or just 1, 1, 1, if you do it with subtraction and division compared to add 1 and then divide, it actually turns out to be the same number of operations, 4 operations. But if you add another 1 here, 1, 1, 1, 1, now if you add 1, you line up 4 zeros and you can just shift those, and it turns out to be 5 operations. Whereas if you just subtract and shift, that would be 6 operations. So we can say that 4 in a row here is the tipping point for when adding becomes more profitable than just subtracting and dividing. So what a lot of people ended up doing for the solution was they just said, well, if you've got 3 or more 1s in a row here, if the bottom 3 bits are 1, then add. Otherwise, if it's a 0, obviously you just shift, and otherwise you subtract. So that's what they did. But that is short-sighted because you're missing some cases. So let me show you the case that you're missing. So let's take a look at this number here, 111011. We're going to use our short-sighted algorithm. We're only going to add if the bottom 3 digits are all 1. So here we don't add, right? So we subtract, we get 111010, then we shift 11101, then we subtract 11100, then we shift 1110, then we shift 111, then we this is 111, so we add, and that's 1000, then we shift 100, we shift 10, we shift 1, and we're done. How many is that? That's 1, 2, 3, 4, 5, 6, 7, 8 operations. Now let's do the same thing but let's take a different approach. We're going to start off by adding 1. So we get 1, 1, 1, 1, 0, 0. Maybe you guys can now see what's going to happen here. So then we shift, 1, 1, 1, 0, we shift, 1, 1, 1, 1. Then we add 1, 0, 0, 0, 0, we shift, 0, 0, 0, we shift, 0, 0, we shift, 0, we shift. So here's 1, 2, 3, 4, 5, 6. No, wait. I missed one in here. Fuck. It was actually 1, 2, 3, 4, 5, 6, 7, 8, and then 9, right? So this is actually 9 operations, but this one is only 8. So you can see here that our rule of just looking at the bottom 3 digits and adding if they're all set isn't going to work. And the reason why it doesn't work is because in the case of this 1, 0, 1, 1, adding 1 will set this like this, right? Which means if you have in here some other digits, some other ones, you start making it tasty. You're lining your shit up for another add later down on the road. So it's short-sighted to only examine these 3 digits. You also have to check to see if you could possibly line up another one down the road. And it turns out, if you do the analysis, you have to examine 4 digits. And the cases for adding are 0, 1, 1, 1, or 1, 0, 1, 1. Let's take a look at this case here, 1, 0, 1, 1. Whether you started off by subtracting or whether you started off by adding, it's the same amount of operations. So regardless of what this next bit is, this is going to break even either way. But as you add more ones here, the adding starts to get tastier and tastier. So the rule is, if it is 1, 0, 1, 1, or if it is 0, 1, 1, 1, or if it's 1, 1, 1, 1, in any of these 3 cases, you are going to add 1. Otherwise, you're going to subtract. Unless it ends with a 0 bit, in which case you shift. Now, of course, the only wrinkle there is you've got to be able to do this with very large numbers. And there's a bunch of ways to go about this here. But all I've done is I created a vector, and it is a vector of unsigned long. So it's a vector of integers, 64-bit integers. So what you can do, well, imagine an int was a 4-digit decimal number. So you could store, up to 9999. So what would you want to do if you wanted to store big, larger numbers? Well, you could stick another int besides that, and now you can store up to, an 8-digit number, up to 99 million, and so on and so forth. You could just add more chunks here of digits to make your storage capacity larger. And that's basically what I've done here, only instead of the chunks being 4-digit decimal numbers, they're 64-bit binary numbers. So if you want to do math with this kind of large number, you're going to have to support some operations. Now, the operations we want to support is we want to be able to, at the very least, we want to be able to add 1, we want to be able to subtract 1, and we want to be able to shift right by 1 bit, which is division by 2. So I added a bunch of operations here. 1 second. So this is shift left by n bits, this is shift right by n bits. This is the same thing, but it returns a new big num instead of modifying the left-hand side big num. And I've also added adding for adding one big num to another. And I have adding for adding a single long to a big num and subtracting. And then increment and decrement, just add a single long to the current big num. So, the operations here, shifting is pretty simple. All you got to do is you go over all the bits, all the chunks, I should say, and you're gonna, this one's shift left. So you're gonna shift it left, and you're also gonna shift in the carry from the previous chunk. So you got a binary number like this, you shift to left, you're gonna be shifting these bits to the left, 1 1 0 0, but you're also going to have this bit shift in from over here. And the way you handle that is, well, if you're shifting left by 1, to find the carry out, what you do is, well, let's say you're shifting this one to the left by 1. So the result of shifting is going to be 0, 0, 0, 0. The carry out is actually going to be the thing shifted to the right by 3. This is a 4-bit chunk. So shifting to the right by 3 gives you 0, 0, 0, 1, and that is the carry out that you can then exclude. You can OR that. This is an OR operation, logical OR. You can OR this with this, and you get 1, 1, 0, 1. So if you want to do the carry out of a chunk of binary bits, you shift right by the complement. So if I'm shifting left by 1, the complement is going to be 3. If I'm shifting left by 2, the complement is going to be 2. So you shift right by the complement, and then you OR that into the thing that you are going to be carrying into. And that's how you do it. So that's what I'm doing here. Check it out. So I set the carry to 0. I shift left by n. I OR in the carry, and then carry is going to be equal to new carry. And carry is just the chunk shifted right by the complement of n, which is 64 minus n, because our sizes of our chunks 64 bits. So 64 by n, you shift that right to get the carry in. You shift left, you OR in the carry from the previous chunk, and you do that for all the freaking chunks, and you've got your shift left. This one here, this test for 64, is if you're shifting left by 64, all you're going to do is basically shift every chunk over by 1. So actually, now that I look at it, this test isn't even necessary, because if you're at 64, if you shift the chunk left by 64, the result here is always going to be 0, because you're going to shift out all the bits. And then if you OR that with carry, 0 or anything is just whatever it is. So this and this do the same thing, and therefore, in the case of 64, n is equal to 64. And in that case, this if statement is useless. So whatever, bit of a brain fart, doesn't matter. Then if you have a carry out from the very highest chunk, that means that you got to add a new chunk to the top. Right, let's say you got 4-bit chunks. You shift this left. This is going to be 0, 0, 0, 0, 0, 0, 0, 0. You're going to get 1 bit out, so you've got to add a whole new chunk in here, and you set that to 1. Or you set it to whatever was carried out. And that's what we're doing here. We're just pushing back the last carry. Yeah. And the right shift is the same idea, only in the other direction. And then these guys are just going to create a new big num and then do the shift on it. Now adding is, it's pretty simple. It's the same idea as your normal adding that you do in grade school. Imagine each of your chunks is 1 digit. All you're going to do is, well, if you got 2 big numbers, so let's see, 7, 3, 4, and let's say 1, 8, 9. And what you're going to do is you're going to add the 2 digits that line up with each other. So 4 plus 9 is 3. You're going to get a carry out of 1. So you're going to add that carry out plus these 2 numbers here, and you're going to get, I don't know, that's a 2. And you get another carry here, and then you're going to get a 9. So 9, 2, 3, I hope. And you're just doing that, but on a bigger scale. Instead of having single digits, decimal numbers, you're going to have 64-bit binary numbers, but the idea is the same, right? Now, the way you detect a carry is, well, if you add 2 numbers here, if you add, let's say, 4 and 9, and the result is less than either of these numbers, that means that there was a carry, right? 4 plus 9, in this column here, the result is 3. So that means that there must have been a carry. So you can deduce a carry by adding 2 numbers together and checking then to see if the old number is greater than the new number. And if it is, that means there must have been a carry. So we set carry to 1, and then next time when we're adding, we add old. First we store the old value. We add old plus the other number plus the carry. And if the old is greater than the result, which we stored back into here, then that means there must have been a carry. So we do that. We loop through all of the digits. Now, if we're adding two numbers and they have different sizes, two big nums with different sizes, what you can do is basically you only have to loop up until the smallest number. So we only have to loop here and here, and that's it. So we add this one 1, and we add this one to this one 0, and there's a carry. But you have to propagate the carry. So you have to keep propagating until there's no more carry. So if this was a 9, for example, you'd add them together, you get a 0, you get another carry, you'd have to propagate that over. And that's what we're doing here. So we're looping. That's not what we're doing. I think I started off doing that and then I changed my mind. Because here I resize left-hand side to be the same size as right-hand side. But then I loop until end, which is equal to right-hand side dot bits. And then at the end, I propagate the carry. Maybe I got a brain fart here, but I don't think this is even necessary. Because if they're the same size, then the final carry should just go into here. It should just, if there's a carry at the end, it'll just be pushed back into the number. But I could be wrong. There could be something I'm missing, but I feel like if I erase this, I'll still get the right answer. We'll try it out in a second. But that's adding. Subtracting. Did I even have subtracting? Yeah, I do have subtracting here, but only for long, not for a big num. So adding a single digit number is basically the same. You just add 1. You add to the lowest digit, and then while there is a carry, you keep looping and propagating the carry. And if there's a carry out of the highest digit, then you have to push back a new chunk. Subtracting equals is similar idea, but in the opposite direction, I guess. I must have copy and pasted because I didn't fucking change this, but this should be keep subtracting while there's a borrow. This carry becomes borrow in here. But it's the same idea, and then if we borrow out of the highest digit and it becomes 0, then we can actually shrink our array, so we can pop back. So that's what we do. And subtract, same deal, and then increment, decrement, just uses these ones up here. To integer, what is this bullshit? Okay, so there's to integer, it just converts to a single integer, but what it does is it only converts the lowest chunk. So it's not a proper conversion, it's a conversion with overflow. So if the number is bigger than one chunk, you'll only get the overflow of the first chunk. A couple tests. If the number is 0, this will return true. If the number is 1, this will return true. If the number is 0, this will return true. Get bits returns a constant reference to the vector. I don't know why, but I put it in there. Get chunk count returns the number of chunks in there. Get low returns bits dot front or 0, depending on whether size is greater than 0. So actually, to integer, I don't know why I added this one, but it's bad. Because what if the number is 0? Then the chunk count will actually be 0. This will be bad. So I added this. I never use it. It shouldn't even be in here. But this one's better because it checks to make sure the size there's greater than 0 chunks in there before it returns front. Otherwise, it just returns 0. Because if you got 0 chunks, that means your number is 0. And count low zeros. This one's a little important. It counts the number of low 0 bits in the first 64-bit chunk. So it'll return the number of trailing zeros in the binary representation up until 64. If there's more than 64 trailing zeros, it returns 64. And it's just a very simple, naive implementation of just shifting right by 1 bit and checking to see if the number is still not 0. So that is all of the big num operations, except for perhaps the most important one, which is the one that converts from the string into the big num. So there's one here that just initializes a big num with a long, unsigned long, and just push that back into the bits. But the one we're interested in here takes a string. And the way it works is it's basically just your basic, if you've done my string tutorial, it's the basic thing that you got in there. For each character in the number, we'll just do a check to make sure that the number only contains digit characters. But you multiply the current big num by 10, and then you add character ASCII value minus 0. And subtracting by 0 gets you the digit value from 0 to 9. And then you just add that to the current number. So every time you multiply by 10, and then you add in another digit, and you multiply by 10, and that will build up your number, your decimal number in binary in our big num. Now, how do we multiply by 10? Because I didn't define a multiplication operation in here. Well, it's quite simple. You shift left by 3, you shift left by 1, and you add those results together. And you might be saying, how does shifting left by 3 bits and 1 bit and then adding together multiply by 10? And it's very simple. Take a number, take a very simple binary number. Let's take the number 1. Shift it left by 3, you get 8. Shift it left by 1, you get 2. Shifting left by 3 multiplies by 8. Shifting left by 1 multiplies by 2. So if you have any number, n times 8 plus n times 2 is equal to n times 2 plus 8 is equal to n times 10. So you can shift and add, and that is a simple way, or not so simple way, of multiplying by 10, or you multiplying by any number you want, basically. Different patterns of shifting and adding will give you different multiplications. So this is a way of, back in the old days, this was an optimization for very fast multiplication and division, but mostly multiplication. And you can still do it today, and compilers will still do it. If you multiply a number by, say, 4, it'll probably just shift it left by 2 bits under the hood. But for us, since I didn't define a multiplication operator, and I figured maybe shifting would be faster, I just did it this way. Turns out shifting isn't faster, but we'll get into that in a second. So that's how I did the multiplication by 10. That is how I did the whole the shindig here. And then all you got to do is implement the motherfucking algorithm. So first of all, we create the big num of bits by constructing with a string. And then we do while bits is not 1. We count the low zeros. And we shift right by that many zeros, and we add that many to the count of operations. Now, if the number of trailing zeros is 0, if we don't have any trailing zeros, then we must have a 1 in the first position at least. So we get the low bits of the number, the low 64 bits, and we're going to check them. So if low, and we already know that the first bit is going to be a 1 from this test here. So now we want to check the second bit. Is the second bit a 1 and either the third bit or the fourth bit? So this will mask out the third and the fourth bits. And if either of these are 1, this will be non-zero. So if this is non-zero, that means if we have one of these bits and we also have this bit, then we must we want to do an add, because that corresponds to our adding case. So we increment bits, otherwise we decrement bits. And we just do this and we count as we go, and there you go, you got your answer. Now, my original testing didn't use the big number file, so let's test this out and see what we get. So here, my naive implementation here does it in about, well, this is about 7.6 milliseconds. This is about 1.7. So we're looking at 9.3 milliseconds. 9.3 milliseconds, not too bad, but there's plenty room for improvement here. Now, what I did, well, you can see here a weird thing. I've actually analyzed the numbers 10 through whatever this number is. Basically, all of the powers of 10 that fit in 64 bits. And I've counted how many set bits there are in this one. Because the number of set bits equals the amount of shift add that you need to do to multiply by that number. So, for example, 10 has 2 bits set, right? The fourth bit and the second bit, and that's why you have to shift left by 3 and by 1 and add in order to multiply by 10. Now, if you go down here, that means that basically to multiply by 10, to shift left by 1 decimal digit, you need 2 bits, 2 shifts. So that's a ratio of 2 to 1. Now, if you want to multiply by 100, you need 3 shifts. That's a ratio of 1.5. And I calculated the ratios here, and I see that the best rate is all the way down here, multiplying by 10 to the power of 19 here. 10 to the power of 19? I don't know what this is, but it's, I think it is. It's a 1 with 19 zeros, I believe. And that requires 19 shifts, and so the ratio is 1. So later on, I figure instead of shifting the entire big num 2 times for every 1 decimal digit, I can build up a 64-bit huge number and then push that into the big num by doing 1 multiplication by 10 to the 19, which only requires 19 shifts. Now, before I make that optimization, I realized one thing here, and that was doing this shift, to add them together, I had to make a copy of the big num. So I shift left by 3, and I put that into a new big num. Then I shift the current big num by 1, and then I add the copy, the shift left 3 copy into the shift left 1. So I have to allocate memory every time for every digit that I'm converting. So instead of doing that, I created a scratch big num, which is pre-allocated, and I just copy into that one, and then I shift left, and then add. So in this case here, we're not doing a shit ton of reallocations. So what I do here is I also estimate the number of bits required given the size, the number of decimal digits, and then I create the big num, and I reserve the amount of chunks required for that many bits. So, well, basically you get 3 binary, let me think here, 3 binary bits, a little over 3 binary bits per decimal digit. So divide the size of the string by 3 will give us a little overestimation of how many bits we need. Divide that by 64, and that will give us an estimation of how many chunks we need. So by doing this, I basically remove a lot of the dynamic allocation from the algorithm, so it doesn't have to new in a bunch of heap memory while it's running. And here we can already see these 2 numbers here, by the way, I don't think I mentioned it before, but this is the parsing time and this is the calculation time. So the parsing time went from 7.6 or whatever it was to 5.2. So we got a decent reduction in time by pre-allocating that memory. Not a huge win, but considering the small change to the code, that's a pretty good win in my estimation. Now, the next thing I did was I basically replaced the mul10 function with a mul power 10, and this one will multiply by some power of 10. And the way it does it is it uses those shift patterns. So what I did was I generated a multiplication table of just how you must shift and add in order to multiply by certain powers of 10. So for example, and these are cumulative, by the way. So to multiply by 10, you shift by 1, you add, and then you shift again by 2 and add. So this would be a total of 3. So shift left by 1 plus shift left by 3. This would be 2 plus 5 plus 6, and so on and so forth, up until 10 to the power of 19 would be right here. And I tested it out by just doing the same thing by multiplying by 10. Then I optimized the parsing logic by, well, while there are 19 or more digits, we basically convert 19 digits into a long, an unsigned long. So that's your basic conversion with multiplication in here. And then we push those 19-digit long into the big num. So we multiply by 10 to the power of 19, and then we add the big long into there. And this one gave us a good speed up. I don't remember how much. It was decent, but we can do better. Because what I realized here is by doing this, you have to actually shift the entire big num 19 times. And what I thought to myself was, well, if I just multiply the entire big num by an unsigned long, that's going to be way faster, right? Because I only have to run over the big num in one pass, whereas I got to go over it 19 passes in order to multiply by shifting. So that is what I ended up doing later on, fast multiply. And in fast multiply, what I did was, well, I created a lookup table. Let me see if I can find it here. Here it is. So I replaced this lookup table here with the shift numbers, which is a basic lookup table of longs, unsigned longs, going from 1 until, 10 to the power of 19 or whatever. And what I'm doing here is now I've got, that's just a table. So now it's just this times pow of however many digits are left. So here it's this times, where is it? Value times 10, right? And this, let me think here. Because as long, how does this work again? Now I'm confused. Right, so as long as there are 19 or more digits left in the decimal number, we build up an unsigned long of 19 digits worth of decimal number. And then we shift over the current number by 10 to the power of 19, and then we add in the new number in there. And then we convert the remaining digits, which is we build up the remaining digits, and then we shift it over by however many digits worth of power that is. And then we add in. Yeah, there we go. Okay, that's how that works. Makes sense to me. And this was way faster. Now, the way we do the multiplication, I mean, I think you guys can probably figure out how to do the multiplication on a like from a single digit number to a big num. So again, looking at our analog here, just single binary digits, like let's say we've got the number, 9, 3, 4. We're going to multiply it by 7. What do? Well, we multiply this one by this one, and this multiplying two single digit numbers gives a 2-digit result, at maximum 2 digits. So this one would be, the low digit would be 8. Put that there. The high digit would be 2. You put that there as a carry. Then you multiply 3 times 7. Low digit is 1 plus the carry is 3. And the high digit is 2. You put that there. You multiply 7 times 9, 63. Add that in there, 65. So this is how you do it. And it's the same as if you're working with chunks in a big num. Now, the problem with this is you want the low and the high part of the result. If you have a 64-bit int and you multiply it by another 64-bit int, the biggest result you can get is 128 bits. But your result, 64-bit times 64-bit number, is going to be a 64-bit number. The C++ standard doesn't have 128-bit numbers. So you're going to lose the top 64 bits. So you can solve this in a number of ways. One simple way of doing it, staying within the C++ standard, is reduce your chunk size to 32. You multiply your two 32-bit numbers together, you get a 64-bit result, and then you just got to shift around to get the high and the low part. But if the C++, not the C++, the x86 64-bit processor has instructions where you can multiply 64-bit by 64-bit and get the full 128-bit result. One of those instructions is called mulx. It's called mulx. And what you can do is you can use an intrinsic to access this instruction, and it just allows you to access this assembly instruction as a function. You have to include intrin.h. And what this lets us do is this lets us do a multiply. We can get the high part, which is here. We can get the low part here, and then we can set the bit at that position, or the chunk, to the low part. Then we can add the high part in, propagate carry, and you keep doing that, setting the low plus the carry, and then the high is going to go up into the next position as a carry. And that's basically it. So we just, an add carry is another intrinsic, because you remember before when we added, let me see if I can find an adding function, but when we added, we had to infer whether there was a carry by testing the number against its old value. And if the number got smaller, that means there must have been a carry. But if you use the add carry intrinsic, you get the carry directly. It's just a little bit of an optimization here. So I could have done this in a number of ways. I could have used 32-bit numbers. I didn't need to use add carry either. But by using this, I figure I got probably at most a double speed increase. At most. Probably a little less than that. But it's faster using intrinsics in this case than it would be to just use standard C++. So I did that, and it gave me a little bit of a boost. And this one got me to, I believe, about 2 milliseconds. I'm not going to test it, but I believe I was down to now 2 milliseconds. So I got from about 9 to maybe 7-ish down to 2 milliseconds by replacing that. And now, because before my performance was dominated by the parsing, but now the parsing actually got faster than the actual processing. So you always turn, when you're optimizing, you always turn your attention to the thing that is running the slowest first. So I managed to reduce that thing down to lower than the next thing. So then I turned my attention to the next thing, which is the processing. And the way the processing works is, well, let me show you here. What we're doing, essentially, is we're only examining the low 4 bits, and we're doing some tests on them to see what we should do, whether we should shift or whether we should add or subtract, right? Well, what we could do is, the idea I got is I could create a lookup table. I could create a lookup table that's just an array, and the array goes from 0 to 15, and that represents our bit patterns from 0000 to 1111. And for each of these entries in the array, I would give the amount of operations needed to shift this thing right by 1. So for example, if it ends in a 0, it's obviously going to be just 1 operation. But if for this one, to shift left by 1, it would be 2. But the idea I got was, this is small potatoes, because what we can do is we can look at a bit pattern like 1101, 0111, and we can say, okay, how long, let me collect my thoughts here. I got to explain this correctly. How many operations would it take to shift this thing right by 5? We can't shift right by left because we don't know what operations we need to take. Once we shift right by 5, our number is now going to be only going to have 3 digits, but we need to examine four binary digits in order to make a decision. So we can only shift right by the size of our number that we're looking up in our lookup table in bits minus 5. No, wait. Minus 3. So for an 8-bit lookup, we can predict how many operations it'll take to move this thing to the right by 5. And that is what, I think that's what I went for in here. So what I did was I created one, let me see, what do I got here? Big num operator. Yeah, that's fine. What did I do? What did Chili do? I created a lookup table class here. And the lookup table has, where is my, there it is, as a vector of cars, and that is the counts. So that is the number of counts required to process an 8-bit number so that it is shifted right by 5. And a lookup in there is just, we just look up into the array. So if I pass in bits, which is just 64-bit, the low 64-bit chunk, it will mask that so that we're only examining the low 8 bits. And then it'll use that as a lookup into a table to determine the count. And we just build the lookup table the same way we process down here. So we build the lookup table with our normal process, but then we do the lookups so we can process, basically we're processing 5 bits at a time. So we can consume 5 binary digits in a single operation and add the operation count into here. And that was my idea. It had some flaws. Let's look at the flaws. Well, before we look at the flaws, I got the idea of you could have bigger or smaller lookup tables, right? So, and a lookup table to examine 8-bit numbers for processing 5 bits at a time would have 256 entries. But what if we wanted a bigger lookup table? What if we wanted to examine 12 bits at a time? That would require, I think, maybe 4,000 entries. I don't remember. But anyways, it would require more entries. So what I did was, instead of having a lookup table like this, I templated it on a bit count. And I made all these things dynamic with respect to the template parameter. So the amount of space that is reserved and the amount, what is it? Let me think here. For example, the mask here. If I can find it, yeah, where's the mask? The mask is also calculated based on the bit count, etc., etc. So I made it templated so that you can have lookup tables of different sizes without having to change a bunch of code. And that's sweet, but it didn't work. It got me wrong answers. So then I examined my code and I realized I was being a dumb idiot. And the reason I was being an idiot is, well, in my code before, so what I was doing was I was just shifting right by 5 and adding the count. But that's not correct, right? Because when you process those 8 bits and shift right by 5, the high 3 bits are also going to change depending on what operations were taken. But shifting right by 5 will not reflect that in the big num. So what I had to do was, in my lookup table, I had to create an entry class. Let's see if I can find it. Entry. An entry stores the number of steps, but it also stores the state of the low 3 bits and the bit that was carried out if there was a carryout bit. So low state is actually 4 bits, and it stores the 3 bits that remain after shifting, and a bit, which is basically saying whether or not there was a carry out. So then when we're building our lookup table, we process 8 bits or however many bits the lookup table is at. And at the end, we store the remaining result, because the way we process this is we take the bit pattern that we're using for that entry in the lookup table, and we just run our algorithm on it. And it is going to run the algorithm until it has been shifted right by 5. Whatever remains, that is going to be the second entry in our entry in the lookup table. And then that remainder is going to be used down here. So you add to count, you do the lookup, you add to count, then you perform the shift by the shift amount, whatever it was. If it was 8 bits, it's going to be 5. Then you set the low 3 bits of the big num, and you do that by doing, what is it? You mask out the low 3 bits of the thing in in our big num, and you OR in the entry low state, that has been masked by the low 3 bits. So you're taking the low 3 bits of low state and you're plugging them into the low 3 bits of our big num. Then the 4th bit is the carry. So you mask out all the other stuff of low state. You only keep the 4th bit, and then you add that into our big num. So this is what is required to process basically do a 5-bit shift. If your lookup table is 8 bits, this is going to do a 5-bit shift process. It's going to look at 8 bits, it's going to shift right by 5, and it is going to fix up the number, and it's going to count up how many operations that would have taken. So we do this, and we do that until the number of bits that are remaining is less than our lookup table size. And then we process the remaining bits, however many they are, just with our normal algorithm. And if we do this bullshit, you will see that the total time taken here is going to be, the first number here is the time to parse the number. So that went all the way down to 250 microseconds. Then here's the time taken to build the lookup table, which is 81 microseconds. And then you've got the time to actually process, 342 microseconds. You add it all together, you get about 670, 680 microseconds. Depends on the run. But yeah, that's it. And you can use bigger or smaller lookup tables. I found that about 11 or 12 bits is the breaking even point. If you do bigger lookup tables, the time taken to generate the lookup table makes the total time slower. And if you do smaller, then you're not getting as much benefit out of the lookup table here. So this one processes 9 bits at a time. It shifts right by 9 bits at a time in this loop, and then the final 11 bits are just processed in here. But yeah, that is it, my friends. That is how Chili achieved supreme victory. And there's a bunch of other ways that I could think of, optimizing this further, but at a certain point, you just gotta say, man, it ain't worth my time no more. And I think that point I have reached. But I mean, if I wanted to further optimize it, I was thinking, right now what we're doing is we're looking up a number of bits in the number. We got a window that we're looking up, and then we're shifting the whole number, to the right by however much, by 5 bits or by 11 bits or whatever. What we could do is, instead of shifting the whole number to the right, all we got to do is shift our window of interest to the left. So now when the number stays the same, we're just looking up different bits in there. So now instead of the operation being an n squared, we can reduce that to an n operation for processing the actual bits. And I mean, it could be possible to, for example, use AVX and multi-threading on the number parsing, but again, it ain't worth my time, so I'm gonna say no to that. But it's something that would be possible if you were interested in. If instead of processing 7,000 digit numbers, you're processing 7 billion digit numbers, it might be something you'd want to look into. But yeah, that's it for this challenge. Obviously, a lot more work than the last one, a lot bigger video for the explanation and everything. But I hope you guys enjoyed it. It seems you did, judging from the amount of submissions I got. And next one that we do, whenever we do it, I'm actually going to do it in a bit of a mini game engine. I'm not going to spoil what it is, but I'm going to give you guys some code, a kind of sandbox in which to build your algorithm in, and then you're going to submit to me just your algorithm part, and I'm going to test them all in the sandbox. So we'll see what that is when the time comes. But until then, I'm Chili, and I will see you soon with some more C++.